Welcome to the Deep Dive. We aim to get you up to speed fast on specialized topics. Today, we're really zooming in, getting granular on one of those materials that honestly keeps modern industry ticking. We're diving into the specs and the secrets, really, of the hashtag 2000S valve lube sealant.
Yeah, this is serious stuff. We're talking about components that are, the backbone of critical infrastructure. This sealant, it's not just making things slippery, it's engineered, designed to work perfectly when things get really rough.
Exactly. Think extreme pressures, nasty chemicals, huge temperature swings.
The worst conditions, basically.
Right. So our mission today, cut through the technical jargon. We want to pull out the key achievements in how this stuff is made
Yeah.
and explain why the folks in the field actually rely on it. The goal is you walk away knowing what the 2000S really brings to the table.
Okay, let's unpack this. Okay, so first off, you got to understand, it does two jobs at once. It's a valve lube sealant, so it has to lubricate, let the valve parts move smoothly, open and close, but at the same time, it has to seal, create a really reliable barrier so whatever's inside the pipe doesn't leak out. It's a tricky balance, high stakes.
And looking at just the basic chemistry, there's something that immediately flags this as, well, a modern product. Even though it's heavy-duty, high-performance stuff, the sources make a point of saying it's synthetic. And, importantly, it's also biodegradable.
That's actually critical. Traditionally, getting top performance often meant using materials that weren't great for the environment. Being synthetic lets chemists really tailor the molecules for the best resistance, the best stability, but adding biodegradability, that tackles a huge operational concern. If some leaks or spills, well, the material breaks down over time, less long-term impact. And that's becoming a major requirement, especially in sensitive areas.
Okay, so regulations probably push the chemistry there, get the toughness without the environmental baggage.
Precisely. It's where performance meets compliance.
Yeah. Okay, so here's where it gets really interesting for me. Let's move past what it is and talk about what it's built to survive. We're talking substances that can literally eat through metal, degrade normal lubricants pretty fast.
Well, the resistance profile for the 2000S, it's really comprehensive. It covers pretty much all the major hazards you'd find in oil, gas, petrochemicals, things like natural gas, mineral oils, light hydrocarbons, LPGs, most aromatics, crude oil, water, even instrument air.
That list, I mean, that's everything from raw stuff coming out of the ground to finished products.
Yeah.
But the sources highlighted two specific compounds that really show its pedigree for, severe service.
Right, and those would be H2S, hydrogen sulfide.
Sour gas.
Exactly. Sour gas, extremely corrosive. And CO2, carbon dioxide. CO2, if there's water around, makes carbonic acid. Also very destructive. So connecting that to the bigger picture, resisting both H2S and CO2 means that this isn't just for clean pipelines. It's engineered for those really harsh conditions. Think wellheads, gas processing plants, places where these corrosive things are just constantly attacking the valve internals.
Okay, so the sealant itself is almost like a shield, a protective layer against these corrosive fluids, saving the expensive metal parts of the valve.
Absolutely. It stops the process fluid, the H2S or whatever, from getting to those metal-on-metal contact points, because that's where corrosion really takes off.
Got it. Now let's switch gears a bit from protection to function, the lube part of lube sealant. It's about making the operator's job easier, right?
Yeah.
So what's the technical trick here? How can it seal so well against something like H2S, but still let a technician, turn the valve handle without needing a giant wrench?
This is where the formulation gets kind of elegant. They've managed to combine two things that seem, well, almost opposite. First, the base lubricant needs to have a light viscosity.
Light viscosity, so it flows easily.
Exactly. That's crucial because it lets you pump the sealant easily into the valve, often under pressure, maybe through long injection lines. If it were too thick, like cold molasses, the injection equipment would just struggle.
Okay, light viscosity means easy pumping, but doesn't light viscosity usually mean less sealing power? Especially under high pressure. How do they square that circle?
That's the clever part. They add moly disulfide. People usually just call it moly. Moly works as a solid film lubricant.
Solid filler.
Yeah. So imagine the valve is under high pressure. The liquid part, the light oil, might get squeezed out from between the sealing surfaces, but the moly particles, they stay behind. They plate out onto the metal surfaces. They provide lubrication even under extreme pressure, and crucially, they help maintain that seal.
And the actual benefit of that solid film, what does the operator feel?
The moly really helps to reduce the valve operating torque. dramatically in some cases. And look, this isn't just some number on a data sheet. This translates directly to, is it a struggle for a technician needing extra tools or leverage to turn that valve? Or can they cycle it smoothly, easily, safely during normal maintenance? It means less strain on the person and less strain on the valve mechanism itself.
That makes a lot of sense. So the light base oil gets it where it needs to go and helps with initial movement. And then the solid moly takes over the heavy lifting when the valve is clamped shut under pressure.
Exactly. Now, this brings up another important question, right? We know what chemicals it resists, but how does the lubricant itself handle the environment changing around it? Wild temperature swings, a good lubricant has to be thermally stable.
And stability definitely seems like a defining feature here. The temperature range listed for the 2000S is just huge.
Yeah.
The sources say it's rated for proper performance from negative 45 degrees Fahrenheit all the way up to plus 450 degrees Fahrenheit, typical range.
That's nearly a 500-degree swing. Think about that. It means
Yeah.
you could potentially use the same product in, like, Arctic conditions, or on pipelines running through a hot desert, or right next to high-temp process equipment. When you're managing assets all over the globe, that kind of versatility makes logistics way simpler.
And there's a backup number too, right, to guarantee that stability. The sources mentioned the dropping point.
Yes, the dropping point. ASTM D566 test. It basically tells you at what temperature the grease structure breaks down and it starts acting like an oil, starts flowing. For the 2000S, the typical dropping point is listed as over 500 degrees F.
Okay, so well above the maximum operating temp.
Right, that's the key takeaway. You've got this significant safety margin at least 50 degrees F above its normal max operating temp. What that means is even if things temporarily get hotter than expected, like a process upset, the sealant should hold its structure, keep sealing, keep lubricating. It helps prevent a catastrophic failure.
Okay. Beyond the performance numbers, what about just quick physical IDs,
Yeah.
things maintenance crews look for?
Sure, the color is easy. It's black. And its consistency, how thick it feels, falls right in that sort of sweet spot for industrial greases. The NLGI consistency number is a 2 typical.
NLGI number 2. For people maybe not familiar with that scale, what's that like? What does it feel like?
Think about smooth peanut butter or maybe standard wheel bearing grease you'd put in a car. It's soft enough that you can pump it and spread it easily, but it's firm enough that it holds its shape. It won't just, slump or run out of the valve mechanism. That consistency helps make sure it stays put right where you inject it.
Right, those are like the fingerprints for quality control.
Hmm.
Okay, but now let's talk about something that might be, well, maybe the biggest stress reducer for the folks actually doing the maintenance in the field: compatibility.
Ah, yes. This is huge. Often overlooked in specs, but critical in practice. Think about it. In a plant, a valve might have some old grease left in it from the last time it was serviced. Maybe it was a different brand, maybe even a completely different type of chemistry, like an old petroleum-based sealant. Mixing greases that aren't compatible, that to be a real disaster.
What happens then when they don't mix well?
While the mixture can fail, the thickeners might react badly. They could separate, leaving just thin oil, or they could harden up, cake up. And if that happens, it can block the small passageways inside the valve, maybe even seize the moving parts completely. Then the technician has a massive job on their hands having to totally flush and clean out the valve. Lots of downtime, lots of labor.
Okay, so the 2000S basically lets you skip that whole potential nightmare scenario. The spec sheet specifically says, intermingling a Val-Tex 2000S with other lubricants or sealants will not have an adverse effect.
That is a massive help for field work and a huge cost saver, potentially. It means the maintenance crews can, generally, apply the 2000S with confidence, right over whatever might be left in there. They don't have to waste time figuring out exactly what the old stuff was or do a really time-consuming, messy purge. It's like the product is designed acknowledging the real-world messiness of field maintenance.
So it pretty much eliminates that risk of, like, cross-contamination failure, which sounds like it could be a common problem with these specialized chemicals.
It really can be. So yeah, this feature reduces wasted material, makes maintenance faster, and cuts down on how long the valve is out of service. Honestly, that one point makes the 2000S really attractive to the people managing these assets.
And just briefly touching on logistics, if you're bringing this into your supply chain, it sounds like it's easy to get hold of.
Yeah, it seems to be available in all the standard industrial sizes, from the small P-packs maybe for a single truck,
Yeah.
all the way up to 40-pound pails, 120-pound kegs, even 440-pound drums for like a big refinery's warehouse. So it fits pretty much any scale of operation. And of course, as you'd expect with something this specialized, the sources mention you should check with the factory if you have really specific or unusual questions about your application. Standard practice.
Okay, so let's try and pull this all together. What does it all mean? If you're the person managing inventory or maybe overseeing maintenance on these complex high-pressure valves, maybe in sour service, what's the core story of the 2000S?
I think the core story is it's high performance, but packaged with operational ease. You get extreme chemical resistance, especially against those really bad actors like H2S and CO2. That's backed up by incredible thermal stability, working across that huge, almost 500-degree temperature range.
And importantly, that hardcore performance is married to things that make life simpler, like the reduced torque from the moly, making the valve physically easier to operate, and that compatibility factor, which just wipes out a major headache around purging contamination risk. So it performs under pressure, but also simplifies the maintenance job.
That's exactly it. That's the synthesis. It really shows, I think, a successful engineering balance.
Mm.
Balancing that heavy-duty resistance, the ability to stand up to almost anything
Yeah.
with those essential user-friendly features, like being biodegradable and being compatible with other materials. It's quite clever.
It really is a remarkable bit of chemical engineering. Shows how material science keeps pushing forward to solve these tough real-world industrial problems. And, that leads us to a final thought, something for you, the listener, to maybe mull over based on what we've discussed. Given that need for light viscosity so it pumps easily combined with the need to resist really heavy, difficult stuff like crude oil and H2S, what kind of specific engineering trade-offs do you think might have been needed when they chose the synthetic base oil, especially to keep it stable and performing across that massive, nearly 500-degree Fahrenheit temperature range? It really makes you appreciate the fine-tuning that must go into a high-spec formula like the 2000S.